Unit 6b will continue our discussion of fluids to now consider moving fluids. Fluid dynamics is the study of fluids in motion. So whereas in the last unit we talked about fluid statics, that was fluids that aren't moving, now we go into the world of fluid dynamics. This means that we'll still need to think about the same variables that were important for fluids like density and pressure, and we'll explain how fluids move through a fluid system like blood flowing through your veins or water flowing through a hose. Throughout this entire unit, we are only going to consider the dynamics of ideal fluids, which implies several assumptions that are baked into these problems. First, we assume that fluids move in entirely smooth layers, or streamlines, so there won't be any mixing of any kind with these fluids. Also, we'll assume that fluids experience no friction. That means that they have no viscosity, they flow with no resistance at all. These fluids have no rotational effects, so there will never be any swirls or whirlpools or vortices. And ideal fluids are also incompressible, which means that they take up the same amount of volume given some mass of fluid. In other words, the density of an ideal fluid is constant throughout the entire fluid. Flow rate describes the amount of volume of a fluid passing over some given amount of time. We use the letter Q for flow rate, and the formula is shown here. The volume that passes divided by the amount of time that it takes for that volume to move will give you your flow rate. Accordingly, since the standard units of volume are meters cubed and the standard units for time are seconds, then the standard units for flow rate Q are going to be meters cubed per second. But you could also imagine other units that are more common, like liters per minute, gallons per minute. For example, if a typical garden hose has a flow rate of 15 gallons per minute, we could convert that to meters cubed per second to get it into its standard units. Another way of representing the flow rate is based on the area through which the fluid is flowing and the speed at which the fluid is flowing. So you have to be very careful not to mix up the flow rate, Q, which is a volume given in some amount of time, and the velocity or the flow speed, V, which is measured in meters per second. So if we think about water passing through some pipe like this one here, it makes sense that if the pipe got wider, if it had a greater area, then the flow rate would increase. And it also makes sense that if the speed at which water is moving through this pipe increases, then more volume would also pass. So the flow rate, Q, can also be written to be dependent on the area of a channel through which a fluid is flowing times the speed at which that fluid is flowing. We use the variable V bar here, or often we'll just write it as V to say an average speed of the fluid flowing through this pipe, because in reality a fluid actually has a mixture of different parts that are moving at different speeds. But since this is an ideal fluid, we're just going to think about the average speed of fluid passing through some channel. And the other idea that's really important for our conversation about fluid dynamics is called continuity, which basically means that the same amount of fluid will be passing through a system at one point as it is in the other point. So for this pipe here, where we have one end that is really wide and another end that is much smaller, if we are to obey continuity, that means that the same amount of volume will be passing through the large end as will be passing through the small end. That means that if our area is greater on the left side here, the flow speed will have to be less. Then on the right side, where our area is smaller, the flow speed will have to be greater, because if we have continuity of flow, the flow rate at one end of the system will be the same as the flow rate at the other end of the system. In other words, we can say what goes into one side of a fluid channel must come out the other side. So this whole continuity of flow idea doesn't really work that well for gases, because gases actually can be compressed. If we were to put continuity in an equation form, it would essentially say that the flow rate at one end of a system is equal to the flow rate at another. And then we can use our equations for flow rate to substitute in for Q and say that the area times the velocity at one end must be equal to the area times the velocity at another end. This also applies to systems where we have a fluid channel that is branching or becoming multiple different paths for the fluid to flow through. Continuity will still be maintained for a closed fluid system, and that means that the same amount of fluid flowing through one end must be equal to the amount of fluid flowing through the other end of the system. So for branched systems, the continuity equation looks like that shown here, where n is the number of branches at that point in the system, A is the cross-sectional area of a channel through which a fluid is flowing, V is the flow speed, And this product will be equal to the product of those variables at another point in the system. So now that we're talking about fluids flowing, we need to think about how their speed will end up changing the pressure. And the pressure in a system actually goes down when a fluid is flowing faster. And that's because a lot of the overall pressure ends up taking the form of kinetic pressure. So this is a term that looks a lot like the kinetic energy. However, instead of mass, it has density in here. And so the kinetic pressure is 1/2 the density of the fluid times the speed at which it's flowing. And this kinetic pressure does not contribute to the overall pressure that you would measure with a gauge or something like that. The faster that a fluid flows, the lower the pressure will become in that system. Now we arrive at Bernoulli's equation, which is essentially a way of calculating all of the different pressures that are acting on your system. It includes hydrostatic pressure, it includes the kinetic pressure term, and it also includes any external pressure that we might measure with a gauge or other device. Bernoulli's equation says that the sum of each pressure term will always be constant for a closed system. And so another way of rewriting Bernoulli's equation is in the same form that we had energy conservation and momentum conservation for. Bernoulli's equation is essentially a pressure conservation law. And it says that the hydrostatic pressure at one end plus the kinetic pressure at one end plus any external gauge pressure or measured pressure, the sum of all three of those will be equal to the sum of all three of those at another point in a fluid system. So Bernoulli's equation would work for systems that have the same flow speed at one end but different heights. Here we can see that when we're down at our reference point where h equals 0, our height will be 0, and that will cause for that hydrostatic pressure term to go away. And then we can think about the pressure at the other side of the system. When we're up at some positive height, some of the pressure will be taken away and put into the form of hydrostatic pressure. And this means that the pressure that we actually measure at point 1, that's P1, that will be some greater amount of pressure than a pressure that we would measure at point 2. Bernoulli's equation also works for systems where the flow speeds are different, but they're at the same height on both ends of the system. So over here, where the area is much greater, that means that the flow speed would have to decrease. The water would be flowing through this pipe slower at the area that is much larger. And the water would be flowing through this pipe much faster at the area where the area is smaller. So as the speed increases at point 2, that means some of the external measured pressure would be taken away and put into a kinetic pressure term. This pressure that we measure at point 2 will actually end up being less than the pressure at point 1 because the fluid is moving faster at point 2. So remember, when we look at Bernoulli's equation, it basically tells us the different ways that pressure shows up. It will either be hydrostatic pressure, it will be kinetic pressure, or it will show up as an external pressure that we can measure. In the previous unit, this pressure was called a gauge pressure. Our new diagrammatic model for this unit is called a streamline diagram, which is a way of representing how fluids move through a system and how fast they are moving. To draw a streamline diagram, start by drawing your fluid system. Is it a river that has water flowing through it? Is it a branched channel of your blood vessels that eventually go from one big blood vessel to many, many small blood vessels? Is it like a hose that has water flowing through it? Whatever your situation is, you need to be able to draw the fluid, including the container and the walls for that fluid. Then you choose a number of streamlines to draw on your diagram. Here I've drawn 5 streamlines, so at the beginning point, I put 5 dots to show where all my streamlines are starting. And you want these streamlines to be equally spread apart at the beginning of your system and at the end of your system. Then you draw your streamline straight through the system until you get to a different area, and you want to make sure that these streamlines are in straight lines that are always equally spread apart, and that you have the same number of lines at the beginning, 5 in this case, and the same number of lines in the end, 5 again. And then the way we use these diagrams is we count up the number of streamlines that are passing through just some given cutout of the diagram. So here I've created this little panel here that I will use to keep track of how many streamlines are passing through the same area on this side and this side. You want for this cutout to be the same size between point 1 and 2 in your system. we can see that I only have 3 streamlines passing through my cutout on this end, and on the other end I have 5 streamlines passing through my cutout. And wherever you count up more streamlines, like over here on point 2, that will imply that the fluid is moving faster. So in other words, the closer your streamlines are together, the faster the fluid is moving, and therefore the lower the measured pressure would be in that area. Streamline diagrams are really useful for thinking about fluids that are moving over some object or around some object. These streamline diagrams can help explain how wings work on an airplane or how sails work on a sailboat. If we think about the same amount of fluid passing from the left side to the right side over an airplane wing, we can see that the streamlines end up being pushed closer together on the top of the wing, and they spread out farther apart on the bottom end of the wing. That means that the fluid is moving faster above the wing than it actually is below the wing, and this causes there to be a pressure difference across the wing. The air on the bottom end has a greater pressure because it's moving slower, and the air on the top end has a lower pressure because it is moving faster. And this difference in pressure is what gives rise to a lift force for objects like airplanes. Pressure is a force divided by an area, so if the pressure is greater below the wing than above the wing, the force that is applied from the bottom of the wing will be greater. This also explains how sailboats are able to sail into the wind. The shape of the sail on a sailboat will cause for fluids to bend around that shape such that there is a lower pressure in the front of the sail than there is behind the sail, because the fluid has to flow at a higher speed in front of the sail than it is flowing behind the sail. So that's our introduction to fluid dynamics. We'll continue talking about fluids in the next unit, so I'll see you in the next one.